Hi everyone, this is Mrs. Guzman. These are your notes for waves. What a wave is a rhythmic disturbance that carries energy through matter or space without disturbing the medium permanently. So that means that this wave, this disturbance, carries energy without permanently disabling or displacing the material that it's traveling through. Some terminology that we're going to work on today is very similar to what we saw in simple harmonic motion. So that's nice. This should make this fairly easy for us to understand. So frequency for us in SHM was the number of cycles per second. And for waves, it is simply the number of waves that pass a certain point per unit time. So you'll see waves per second used for frequency. Again, like in simple harmonic motion, we measure this in hertz, Hz. Period is still the time that's required for one cycle, and in this case it will be for one wave. These two variables are inversely related to one another. If you know one, you can take the inverse of it to get the other one. Some types of waves that we have is electromagnetic waves. These waves do not need a medium to travel through. So these are the waves that are able to travel through space where there's no atmosphere. So things like X-rays, gamma rays, radio waves. There are several types of electromagnetic waves that we'll discuss. They can travel through anything. They all travel at the speed of light, which is 3.0 times 10 to the 8th meters per second. Mechanical waves do need a medium to travel through. So this would be sound is a good example of a mechanical wave. Transverse waves travel perpendicular to the direction of the disturbance. So if we look at the animation, we see that the energy is carried horizontally from left to right. The disturbance, though, is vertical, up and down. So this is perpendicular to one another. So this is a transverse wave. A good example is if you have a slinky and you flick your wrist, the wave travels down the slinky, but the amplitude of the wave, the height of the wave, is perpendicular to the direction that it travels in. So when we have a wave, we can have the displacement of the wave and then the amplitude of the wave. The amplitude is measured from rest or equilibrium position to the highest point. And not all waves have similar amplitudes. So the displacement is just how much the wave has been displaced. They are not always the same. For longitudinal waves, these waves travel in the same direction or parallel to the direction of the disturbance. So if we had a slinky that we had resting on the floor and we bunched up a bunch of the coils and then let it go, the compressions would travel through the slinky to the other end. There would be no actual movement of the slinky itself other than the coils traveling to the other end of the slinky. So we have compressions, and you can see from the diagram that this is going to be where the coils are all bunched up together. So think of yourself like compressing any type of spring. A rarefaction is where the stretching occurs. So one wavelength, the distance from one point on one wave to the same point on the next wave would be measured in this fashion, as you can see from the diagram. So wavelength is the distance between two identical spots on a wave. You can measure this at several different points. You get to pick. I would pick whatever is easiest for you. The crest is the highest point of the wave, and a trough is the lowest point of a wave. The amplitude is from equilibrium to either a crest or a trough. So amplitude is going to be measured from equilibrium to the highest point or from equilibrium to the lowest point. The period, again, is the time it's going to take for one wave to pass through. So this is the time it takes for one wavelength. And then frequency in hertz is the number of complete waves that pass in a second. To determine wave speed, how fast a wave is traveling, it's really the rate at which this wave moves energy past a certain point. We use the wave speed equation, v equals lambda f. Lambda represents wavelength and f represents frequency. If you're using wavelength in meters and frequency in hertz, this will give you a unit for velocity of meters per second.